upgrade their knowledge. It is my pleasure to introduce today's speaker, Dr. Indira R., Professor, Department of Mathematics, Nitte Meenakshi Institute of Technology, Bangalore. She has been teaching and research experience of about 20 years. She has obtained PhD from Bangalore University in the year 2001. She has published about 30 research papers in peer-reviewed international journal and guided 5 research students towards PhD under VTU. 4 students are currently working under her towards their PhD under VTU. Now I request to Professor Indra Madam to take over this section.
Good morning, everybody. Am I audible?
Yeah, good morning, ma'am. You're audible. Welcome.
Yes, ma'am. I'll start the session.
Yes.
I'm going to speak about Markov process and applications of Markov process. Before starting, let me try to tell you what is a Markov process. Now, there are so many events happening around us every day. Most of the things we have, it follows a definite rule. If we take something like movement of sun or movement of moon or planets, something like that, every day how it moves is under certain rule. It is a deterministic process. It has a definite rule to follow. We can always say what is going to happen next. It always follows its own path. Nothing is going to change. But let us assess something else, the pattern how we travel to a particular place. We every day go to office, we go to market, we go somewhere else. So there is a particular pattern. We usually follow the same pattern. But there is always a chance that we'll deviate from what we are doing. There is no definite rule for us to follow. Let us assess how weather affects. Today's weather, it is very sunny. Usually we expect the same thing to be tomorrow, same thing to be day after tomorrow, like that, and suddenly it will become a rainy day. So here, if we say how this pattern is changing, I don't know how it is going to change, but there is a pattern. Any event which keeps happening again and again will start following a pattern. But it is not 100% sure that this pattern is like this. We cannot design this pattern, but we can predict. Up to 90%, this is going to be true. Up to 100%, this may be true. But it may be true only 50%, something like that. So there is something where a probability arises. It is not always definite, but there is a chance of happening. If I want to say tomorrow, is it going to rain? I will say there is a chance, 50-50 chance that it may rain. Or I may say there is only 1 out of 4 chances it will rain. I can't say it is definitely going to rain unless already there are some signs where we can predict something. So prediction of weather is an uncertain process, but we can predict because we have a pattern which is almost always true. It follows some pattern to 90% efficiency or 50% efficiency, something like that. So whenever events keep repeating, we can assess using some probability associated to what is going to happen next. And when we try to assess something like this, whatever is happening today is the basis for us to predict what is going to happen tomorrow. So today's events are going to affect tomorrow's. But I need not know what has happened yesterday. Based on what is happening today, I can predict what is going to be tomorrow. So I can make a chain of events. So if we process this properly, this is going to help us in predicting many things and building many models where process is not 100% certain, but true to the good extent. So we'll try to assess this. And let us try to define what is Markov process, how these concepts are going to help. Now let us see why we study Markov process. I told you a chain of events can be assessed, So this chain of events, if today's event is going to affect tomorrow's event or current event is going to affect the next event, then we say that is a Markov chain. So that is the basic definition of Markov chain. Let us see why we need this, what is its actual definition, and some examples, some concepts related to that, and some applications. So that will be the pattern of my lecture today. So now, why study Markov process? What is the use of studying? Usually, many different fields this can be applied. Some everyday events also can be predicted using this. Today, if I'm having a pattern of getting up at 6, tomorrow I will get up at 5 only. Day after tomorrow, it will be at 7. Some pattern I have for all the 5 days, 6 days of the week. Sunday, I will just leave it. So this pattern, if I want to predict what is a probability that I will wake up at 5 after 10 days, I can build that as a process and attach some probability distribution to that and time concept to that, so that it is called a process and it keeps on repeating. So this is the kind of things which can be modeled through Markov process, and it is very easy to handle a Markov process. Very easily we can convert this to a graph. I think you are familiar a little bit about graph theory. So Markov process is basically based on probability distribution, can be expressed in terms of matrices, which can be converted to graphs and can be easily studied. So that's one reason why Markov process is usually used. It will also lead us to develop algorithm like optical character recognition, speech to text systems. Some of the examples I've taken. So where these kind of things can be used, Markov process can be used. So let us see what we can do with this. Let us come to study some background, why this thing is used or how this is developed. Now we are all familiar with probability theory. What is probability? Can anyone answer me what is probability? What do you mean by probability? Need not give me the definition, just the meaning of probability.
May or may not.
Yes?
May or may not.
Okay. So it is a chance. It may be true, it may be false, or it may happen, it may not happen. So there is always a chance of happening. So we know what is probability. We define it as number of events which are favorable or number of trials which are favorable divided by total number of events. So now here in Markov process, to begin with Markov process, probability is a very important concept. So if some event is happening, probability of that event can be easily calculated. Now all possible cases of that event, if we consider, we develop what we have a set along with its probability. We can associate some more values with that and build a probabilistic distribution. You have been familiar with probability distribution. So most of our study of probability has dealt with independent trial process. These processes are basics of classical probability theory and statistics. Here I am trying to differentiate what is a classical probability theory which you are studying independently, and then we try to connect it to what is modern probability theory. There is some difference. In classical probability theory, each trial is taken to be independent. Independently, we conduct many chance experiments. Many experiments we try to conduct. We have seen that when a sequence of chance experiment forms an independent trials process, the possible outcomes of each experiment are the same and occur with same probability. So if you're saying I toss a coin and I want a head to come, it's always half. However, number of times you keep the trial, the repeated trial gives you same probability. So that is in the classical probability theory. The knowledge of outcomes of previous experiments does not influence our prediction for the outcome of the next experiment. So here, the same thing. If I toss a coin, head or tail might come. Last experiment, if I had got a head, I will not be predicting that I will be getting a tail this experiment. So these previous things are forgotten and new things are again experimented. This is how classical theory was being understood, was being used. But what happens in modern theory? What is that has changed now? We'll try to see this. Modern probability theory studies chance process for which the knowledge of previous outcome influences prediction for the future experiment. So if I want to say something like a DNA process, I should know something before I start predicting. If I want to predict weather for the next week, I have to have a knowledge of what was the weather this week, previous week, so many weeks to predict what is going to happen next. These kind of things are studied now, for which the previous outcomes have an influence on our study of the future outcomes. So that is where the things, the concepts basically have changed. So in 1907, that's when this particular Markov process began. A. Markov began the study of an important new type of chance process. In this process, the outcome of given experiment can affect the outcome of next experiment, and this type of process is called Markov chain. Now here, a particular event is happening repeatedly, and current event, some outcome is coming, it is going to affect what will happen in the next outcome. So this is the kind of chain of events which is going to happen, and this is based on time. This is attached to time. So it is called a process, and since it is a chain of events and whatever outcome is coming is discrete, we call it as a Markov chain. And today I am concentrating only on discrete time and discrete type of events. So let us move forward and try to define what is a Markov chain. We have set of states, S1, S2, etc., Sn. N number of states are available to me. States is an outcome of an event. So there are some N events happening and all the outcomes I have collected, and we have state space S. The process starts with one of these states. I do not know which state is the beginning. So it starts with one of them. And moving from one state to other, it is going to change its state. Today, if the outcome is now something S1, next outcome will be S2. So it is going to change each time the experiment is repeated. So there is a change from 1 to 2, 2 to 3, or whichever order that is specified. Each move is called a step. If the chain is currently in state Si, it moves to Sj in the next step, then there is a probability that it will change to that particular state with the probability Pij. So if today is a sunny day, tomorrow it is going to become rainy, day after tomorrow it will be snow. Like this, if there are 3 events, so probability that from sunny to rain, there is a probability called Pij, P12 say, and that probability has to be worked out. So it keeps changing from each state every day, move at every step, and some probability is attached to each change. This probability does not depend upon which state the chain was in before the current state. So Pij will not actually is based on what was before. It change from sunny to rainy will be always same probability. It doesn't depend whether first day was sunny or 10th day was sunny, like that. The probability that next day is going to become rainy is what is defined by the probability, say 0.5 or 50%, something like that. So now this is the situation where a Markov chain can be predicted. A stochastic process
Audience, please wait. Due to some network issues, Madam will join again. Please wait. Yes, Indra Madam, please go ahead.
network disturbance was there. So I think
Okay,
I'm
no
audible
problem.
now.
Please.
The probability of xn plus 1 being the probability of xn plus 1 assuming a value j depends on xn assuming a value in. The previous events are not going to affect. That is when we can define a Markov chain. And this probability Pij is called as transition probability. We are changing from state I to state j. So in a time n, so the probability which results is called as transition probability. So now there are so many events present, and every time from I to j it is going to change. So if we collect all the events, if we collect all the probabilities which are possible, so we will have a set of values which can be arranged as a matrix. So this matrix of the probabilities is called transition probability matrix, where every Pij is a probability that I changes to j. So possible values of xj from a countable set is called state space of the chain. The set is collecting all possible values of the particular experiment is called state space, and state space is finite. Markov chain will be homogeneous. The transition probabilities are constant in a particular time. The transitional probability can be represented with the matrix P of Pij. It is called transition matrix and whose elements are the probabilities. So probability has a value which is between 0 to 1 only. It could be 0, it could be 1 or fraction, positive values only. So that pattern has to be followed for this matrix also. And sum of the values of each row is going to be 1. So if I just add over I, Pij, it will give a value 1. And I will, with that property, the transitional probability matrix is defined. So if P gives one step transition from I to j, j to k, or 1 to 2, 2 to 3, 3 to 4, so on. Then if I keep on making this transition after certain number of steps, 1 would have become changed to 7. So transition from 1 to 7 is not happening in one step. It is happening in 7 consecutive steps, and we can predict what is the probability. So x bar n will be the probability distribution at a time step n. The vector whose ith component describe the probability of the system to be in I state at a time n, then probability of xn equal to I can be calculated. So xn plus 1 will be probability matrix into x of n. This is known. Next step, we need to multiply by the transitional probability. So multiply again use the same pattern. Xn plus 2 will be p into xn plus 1 or p square xn. So we go on doing this. It will be n number of product of p starting from the initial distribution. So this is how transitional probability for a nth step can be calculated. Now we'll take an example. Now just look at this figure. There are certain compartments written. Let us assume that these are rooms with some doors. They are connected. So from 0 to 5 it is marked. We are starting at 2. We are going to put a mouse in this place. A mouse will not stay in its place. It keeps wandering unless it has got something to eat or something to do. So we'll assume that we put a mouse in the entrance here in the compartment 2. Then some paths are written. From 2 it can go to 1. From 2 it can go to 4. It will not stay here. It will either move to 1 or it will move to 4. The probability that it goes to 1 will be same as probability that it goes to 4. We cannot restrict the mouse to have this particular pattern only. So we'll assume that the probability to move in whichever path is equal. So if it goes from 1 to 2, same probability, it will move from 2 to 4 also. Assuming that it goes to 1, there are two possibilities. The arrow outwards show where it can go, arrow inward show from where it can come. Now 1 to 1, it may keep on roaming within 1 only, that possibility is there, or it may move back to 2. So if it comes to 1, it has no chance of escaping out of the maze. It has to go back to the start. Okay, the probability of coming back to 1 and going back to 2 is same. So both will be half-half. Now it comes back to 2 only. So it has to go to 4 or it has to come back to 1. So it will have the same choice again. It comes to 4. At 4, it has only one chance to go to 3. So it will come to 4. It will go to 3. At 3, there are so many choices. It can go to 1, get stuck there, or go to 1 and go back to start, or it can directly go to start, or it can move to 5 and it again can get stuck, or go to 0 and escape. If it goes to 0, then it is certainly going to escape. So this is the situation. Now how we can develop a Markov process and what is a matrix that we are going to develop? Let us see in the next. Now this is the situation. Now whatever I explained, I put in the numbers here. If it is at 2, it can move to 4 and 1 with equal probability. So there are 2 chances. So probability will become half. Then if it is at 1, it has 2 possibilities with equal probability. So it is again half. Comes to 3. It can go to 1, 5, 0, 2. There are 4 possibilities, equal chances. So each chance will be 1 by 4. So 1 by 4, 1 by 4, 1 by 4 and 1 by 4. If it comes to 4, it can only go back to 3. So the probability is 1. Completely, that is the only chance it is having and it cannot stay in 4. There is no arrow pointing like it is there around 1. So it cannot stay in 4. It has to go to 3 only. It is complete possible chance. So it will be 1. So if it goes to 5, again it will be stuck in 5. It will not come back. There is no other path to go from 5. So probability that it stays in 5 will be 1. If it comes to 3, it can move to 1, 5, 0 or 2 with equal probability 1 by 4. Again, if it comes to 0, it is going to exit and it will be out of the maze. So the probability that 0 stays is 1. So this is the probabilities associated with each time change. Each step changes that is going to happen here. Each transition that is going to happen here. So now we'll just learn few more concepts. A square matrix is stochastic if all entries are negative and each row sums up to 1. So if I consider transition from 1 to 2, I will be having half. Transition from 1 to 0, 0, 1 to 3, 0, 1 to 4, 0, 1 to 5, 0. So from 1, all the transition will be like this. To 0, it is 0. To 1, it will be half. To 2, it will be half. 3, 0, 4, 0, 5, 0. So it is 0 plus half plus 0 plus 0 plus 0. So it will be 1. So each row will be 1 like that. I will show the matrix later. A transition matrix is a stochastic matrix. Whatever probability matrix we are going to develop, probability is an entry which is non-negative and less than 1. So each line sums up to 1. P is stochastic and all the powers of P will be stochastic. Eigenvalues of P will be smaller than 1 because the probability itself is a value between 0 to 1. So these are the properties which are associated with transition matrix. Now let us learn something about the states. Now here there are 5 states, 1, 2, 3, 4, 5 and 0. So each state has some properties and each state we can associate some concepts. Let us see what they are. A state J is set transient if Fjj is less than 1. A state J is recurrent if Fjj equal to 1. A state J is absorbing if Pjj is 1. Let us see here. From 5 to 5, if it is in 5, change from 5 to 5 itself will be 1. So it is a recurring state and it is an absorbing state as well. It is not, it is an absorbing state provided it is in the diagonal place of the matrix. We'll worry about absorbing in another example. Now here from 5 to 5 keeps repeating. So it is a recurring state. Whereas from 2, it moves to 1 or 4, it keeps changing. Probability from 2 is always less than 1. So it is a transient state. So let us assess other things with some other examples. A recurrent state J is positive recurrent if expectation of Tjj is finite. Now expectation we are not studying much in the lecture I have developed here. So we will not worry much about this. We will just try to see what are the types of states which are occurring. Now we'll come back to the same example. Now I have a matrix along with that. Just observe. From 0 to whatever I have written in the first column, they are the basic states which are present now. 0 to 5 on the top of the matrix is a state which it is going to occur in the next step. Current step, next step. So from 0 to 0, if it is in 0, it is going to be 0. So it is 1. From 0 to 1, there is no path, so it is 0. From 0 to 2, there is no path. So all other things, from 0, there is only one path to itself, so everything else is 0. Now this 0 has 1 as entry in its diagonal place, so 0 is absorbing. Now 1. We'll come to the state 1. From 1 to itself, it's only half. From 1 to 2, it is going to be half. It cannot keep on staying at 1 for a long time. So this is a transient state. Whereas 4, it just moves to 3. There is a transition. Still, it is not going to be the same state. So it is transient state only. 5 is a recurring as well as absorbing state, where the probability is 1 when 5 changes to 5 itself and no other changes occurring. So this is the concept about states. Let us try to learn some more concept. A discrete time Markov chain is said to be irreducible if and only if a state J can be reached in finite number of steps from any other state. Now here there is a example given. There are 4 states. From 1 I can go to 2. From 1 I can go to 1 only. No other state I can directly go. But if I want to come to 3, I have to pass through 2 and then come. That is possible. So I need 2 steps to come to 3 from 1. If I am at 2, I can go to 1, 4 and 3, all the steps. I cannot come back to 2 directly. I have to go to 1 and come back to 2, or I have to go to 3 and then come back to 2. From 1 to 1 itself, it is possible. 3 to 3 itself is also possible. Again, from 4, I can go to 3 and 1. Coming back to 4, I need few more steps. But wherever I am stuck, I can reach the other step in few transitions. It may not be one single transition, but after few transition, I can come back to any of the particular steps. So I can reach from J to I or I to J in finite number of steps. So it is irreducible. It has a strongly connected graph. All the points are connected. Now, a state J is said to be periodic if it is visited only in a number of steps which is multiple of an integer d. So, a state becomes periodic if it is visited again and again. If it is visited in few number of steps. Now here from 1 to 3 we go, then come to 4 and then to 2. Then we go back to 3, come to 4 and then to 2. It keeps on happening like that. So a state with self loop transition is always periodic. There is a loop here which keeps repeating. After 3 steps, you come back to 2. After 3 steps, you come back to 1, like that. A state J is aperiodic otherwise. If it does not come back after certain number of steps, then we say it is aperiodic. Canonical form of a transition matrix. This helps in studying whether a particular system is going to stop after some time or it is going to recur infinitely. So here, first part of the matrix is a change from transition to transitional probabilities. That is states which are transitional to states which are transitional, and from transitional states to from absorbing states to transitional, and absorbing states to transitional state again, and Q is from absorbing to absorbing. So this is kind of partition we make in the matrix so that we can find out which states are changing, which states are absorbing, and we can also assess how many steps are going to take for the whole matrix to become absorbed or the whole chain to become absorbed. Let us see an example later. Few more concepts we'll try to learn. A state J is said to be reachable from a state I if there is a path from I to J in the state transition diagram. If I write the diagram, there should be a path starting from I to reach to J. So here, if I take this example, if I want to come to 3 from 1, there is a path. I go to 2 and then come to 3. So there exists a path. So it is reachable. 3 is reachable from 1. A subset S of states is said to be closed if there is no transition leaving S. Now, if I take part of this loop, if I take this part of the loop, if something is in this loop, it should not leave this loop and come out. Here there is no such loop. But if such a loop is present, we say it is closed. A closed set is irreducible if all states are mutually reachable. In a closed set, if we are able to reach from each point to any other point, then it becomes irreducible. Now we come back to the same example. What is the probability that mouse is in room 2 at time 4? After 4 steps, it starts at 2. In the first step, it either goes to 1 or goes to 4. Second step, from 4 it has to go to 3. If it is at 1, it can be in 1 only or come back to 2. From the third step, if it is in 3, it will come back. If it is already in 2, it will start moving out. So depending upon this type of transition, if I want to find fourth time, I have to multiply this transitional probability matrix with the initial distribution and find P22 after 4 transitions. Now that is what is explained here with formula. Fj after Fij after n is the probability of going from I to j in exactly n steps. Probability of going from I to j in a finite number of steps, Fij is summation n going from 1 to infinity, Fij of n. So similar approach can be used to determine average time taken for going from I to j. The probability of being in a state is defined by pi I, which is vector probability distribution. Now we are concentrating on something like staying in 2 only. So if that particular row vector is considered, I will be able to assess what is the change happening in that row. So that probability distribution is called vector probability distribution over a particular state space at a time n. The probability distribution depends on the matrix and initial distribution pi of 0. If I consider mouse staying at 2 in the beginning, the probability will be 0, 1. It will be 0 for 0, 0 for 1, 1 for 2, and rest will be 0. So it is 0, 0, 1, 0, 0 will be the initial probability vector. Some transitions are going to happen, and coming back to 2 will happen say after 2 steps or 3 steps. So that distribution can be found out by multiplying by P. So that is what is being explained here. Pi after the distribution after n number of steps is initial distribution multiplied by P to the power n. Now if n goes on increasing, will this pi converge or diverge or will become 0? So depending upon that, we can decide what is the kind of process that is happening. Actually, the distribution will converge and converge to a limit which depends on the initial distribution. It depends on where it is starting, and it will converge to some particular vector after a large number of times. So this particular vector which is reached is called a fixed probability vector or steady state distribution. So now we'll see certain examples. Now there is a state n plus 1, the state n. It is changing from state n to state n plus 1. So probability of changing from S1 to S1 is P11, so on. So here 1 to 1 is probability 0.65. while 2 to 1 is probability 28, which is mean from 1 to 2, if it is changing, it is probability 0.28. From 1 to 3, if it is changing, it is 0.07. And you can add all the 3, you get 1. All the entries are positive. And you look at this figure. From 1 to 1, there is a path. 1 to 2, there is a path. 1 to 3, there is a path. Similarly, from 2 to all the 3 points, there is a path. From 3 to all the 3 points, again, we have a path. So every state is reachable from every other state. So it is irreducible. And you can observe that all entries are positive. There is no 0 present here. So one more example we'll consider. A meteorologist is studying the weather in a region. He said to classify each day as simply sunny or cloudy. After analyzing several years weather records, he finds a day after sunny day will be sunny 80% of the time, cloudy 20% of the time. A day after cloudy day is sunny 60% of the time and cloudy 40% of the time. If it is sunny, we say this is state S. From S to S, it's always 80%, so 0.8 probability. S to C, it will be 0.2 probability. S to C to S, it will be 0.6 probability. C to C will be 0.4. So from state 1 to state 2, it is going to change only 20%. State 1 to itself is 80%. State 2 to itself is 40%. 2 to 1, it will be 60%. So the matrix can be built as 0.8, 0.2. You can observe again, each row adds up to 1. All the entries are positive. Now a regular matrix, we consider A, there are some zeros here. From first state to third state, there is no direct path. But if I take powers of A cross A, if I consider, now there is a path. So if this is possible, we say the matrix or the transitional probability matrix is regular. If you consider B, again there are some zeros. You go on multiply, some zeros are going to occur. If there is 1 in the diagonal place, the matrix or the process will be an absorbing process. Those values are going to recur. There is some change happening in the first row where there are some transitional states from 1 to 1, 1 to 3. 1 is changing, whereas 2 is not changing, 3 is not changing. From 1, it can change to 1 itself or 3. So the probability keeps varying each time. And you can observe it is assuming it's going to become 1 in the place of 3 here. From 1 to 3, the value is increasing. From 1 to 1, it is decreasing. So process is going to stabilize, but it is not going to become anything like this. This is going to become absorbing. It's going to stop after some time, and it is going to stop at the position 3, state 3. So this is not regular. This is regular, keeps changing every moment, and it is going to stabilize, become a stable matrix after a long time. But here the process is absorbing. It is never going to become regular. Now we'll take this example, a drunkard walk. A man he's a drunkard, so he is never going to behave in a definite way. He's erratic. So if we leave him somewhere in corner 2, he will either move forward or backward, whichever direction is possible. He doesn't have any particular rule to move. So a man walks along 4-block stretch of a park avenue. He is at the corner 1, 2, 3. He walks to left or right. There is only possibility that he can go to left or go to right. So both will be equal probability. He continues until he reaches corner 4, which is a bar, or corner 0, which is home. So if he goes to 0, he gets stuck there. If he goes to 4, he will sit there. It is a bar. So now move on. So 4 or 1, it is going to stop. Everywhere else, it can change to any other state with equal probability. So let us see what will be the corresponding matrix. So from 0, he doesn't move out. So 0 to 0 will be 1 and everything else will be 0. If he comes to 0, he will not walk again. So it is 0 to transition to any other state. From 1 to 0, he can move. From 1 to 0, it will be half. 1 to 2 will also be half. So it is half and half. Rest will be 0. Similarly, from 2, he can move to 1 or 3 with equal probability. 3 to 2 or 4 is possible. But if he comes to 4, again he gets stuck. He will not move out. Rest everything will be 0. So you can observe there is 1 occurring in both diagonal positions. So 0 and 4 are absorbing probabilities, absorbing states, whereas 1, 2, 3 are changing, so they are transitional probabilities. I mean transitional states. 1, 2, 3 are transition states, 0 and 4 are absorbing states. So since there are two absorbing states, the chain is going to stop after some time. It's either get absorbed at 0 or get absorbed at 4. So it is called as absorbing chain. Now if I want to write the canonical form of this, I collect all the transition states to transition state probabilities as Q, transition to absorbing as R, absorbing to transition as 0. This is not going to happen because once it is absorbed, there is no change happening. The probabilities will be 0. Absorbing to absorbing will always be an identity matrix. So same matrix I have rewritten here. 1, 2, 3 are the states which are changing. So corresponding probabilities. Now this particular matrix 1, 2, 3 to 1, 2, 3 is going to be defined as Q. From 1, 2, 3 to 0, 4, there is some possibility of changes. So this particular 2 cross 3 matrix, 3 cross 2 matrix is R. This 2 cross 3 matrix is 0. From absorbing to transition, there is no change happening. From absorbing to absorbing, it is the identity matrix. So same matrix, we are partitioning into 4 and we are going to concentrate on the transition that is happening and try to find out how many steps it needs to become absorbed. So I'll consider time to absorption. N is defined as I minus Q inverse. Q is 0, half 0, half 0, half 0, half 0. I minus Q will be 1 half 0, half 1 half. 1 minus half 0, minus half 1 minus half. 0 minus half 1, that will be I minus Q. Its inverse we are finding. And this is what we get as the inverse. You can find the inverse and verify. Now, T is N into C. C is a column matrix which is having all entries 1. C is a matrix which is going to have all entries as 1. T into this will give you number of steps taken for that particular state to absorb. This is state 1, state 2, state 3. So if we perform this operation, state 1 is going to take 3 steps to become absorbed. State 2, if the process is in state 2, it will become absorbed after 4 steps. If it is in 3, again it's going to take 3 steps. So this is time or number of steps taken to absorption. Now let us learn some applications. There is application in physics, there is application in chemistry. Chemistry is some protein chain, DNA chain, all that you can define with Markov process. Testing, speech recognition, queuing theory. Markov chain is very much useful in queuing theory. There are some internet applications. Genetics, it is very important. Markov text generators are important to find DNA sequences. So many applications are possible. So let us try to see some simple applications. Everything is not, it is not possible for me to cover. Some simple application I've considered. Auto insurance risk. Auto insurance you make. So you know about the insurance. Based on a company data, a motorist is currently high risk, has 60% of chance of being denoted high risk again when the policy renews, 40% chance of being moved to low risk. Now a motorist is making insurance for the first time. He is considered to be high risk. Again, if he is after 1 year or 2 years, he is renewing the insurance, his chance of being at risk reduces. So 60% and 40%. A low risk driver, if somebody is at this year, a low risk driver, he has 50% of chance of moving to high risk category, maybe due to some problem, and 85% chance of remaining in low risk. So a matrix is possible. If high risk and low risk are taken as two states, H and L, from H to H, it will be 60, H to L, it will be 40, L to H, it is 15, L to high will be 85%. 15%, sorry, L to high is 15%, L to L is 85%. So that creates a matrix, and this kind of things can be assessed, and we can predict after say few more renewals what will be the situation. So a probability tree can be built. So this is one of the application. So same thing is given here as a diagram. High risk and low risk are the two states, changing states. So the probability associated from high to high is 0.6, high to low is 0.2, low to high is 0.15, low to low is 0.85. So a matrix, transition matrix can be provided and can be assessed. Now consider a true processor computer system where time is divided into time slots and operations as follows. There are two processors. There can be one job or two jobs, zero jobs. These are possible. If both the processor may not be working, so zero job is there. One of them may be busy. Both of them may be busy, and third may be in waiting. Beyond this, we cannot process. At most, one job can arrive during a time slot, and this can happen with probability alpha. Jobs are served by whichever process is available. If both are available, it is given to processor 1. Both processors are busy, job is lost. When a processor is busy, it can complete the job within probability beta during one time slot. If a job is submitted during a slot, both processors are busy, but one processor completes a job, then job is accepted. This is the pattern. You can see there is a probability of alpha that a job comes. There is a probability beta that a job is completed. So we can see if states are taken as zero job, one job, or two job, we can form a Markov process and try to assess this. So you can see there is a probability A job arrival, D job departure, feasible event set, X is 0, then probability of X is A. If X is 1 and 2, then probability of X is A and D. So this kind of Markov chain can be set. From 0 to 1, there is a probability of A. 1 to 0, there is a probability of D. D is the job departure, that means job is completed. So 1 to 1 is a probability that it will be A and D. So sorry, it will be A by D, so on. So Markov chain can be constructed like this. If there is a state A, probability to itself, it will remain in the same state. No job will come. The probability will be 1 minus alpha. Probability of getting a job is alpha. So not getting will be its complement 1 minus alpha. One job comes, then processor 1 will become busy. It is alpha. then processor 1 will be busy provided one job gets completed, other job comes, or one job itself keep happening. So at 1 P11 it will be not a job being not completed and one job being other job not being allotted plus alpha and beta. So this is the situation for one. Then two jobs, there should be first job being in the process and a second job occurs. Probability that 0 to 2 is not possible. 0 to 2 directly we are not going, so it will be 0. P11, remaining at 1 itself is this probability. Changing from 1 to 2, alpha is still being done, is not completed. One more job comes, so it is alpha into 1 minus beta. Staying at 2 means 1 is also being processed, 2 is also being processed. So here the probability, both the jobs are not completed. So it will be beta square into 1 minus alpha. It will be alpha into 1 minus beta. From 2 to 0, it will be both job being completed and one more not coming, beta square into 1 minus alpha. So this is the complete process. So Markov chain can be constructed if alpha is 0.5, beta is 0.7. This Markov chain is possible. So some applications I'll show from a book. I'll move fast and try to cover this. I will not go into detail. I'll just tell you where and how it is applied. Now here, you can see a DNA sequence.
Sorry, screen is not visible now.
Oh, okay. Okay, 1 second.
Okay.
And now it's visible, I think. Is it visible?
Yes, madam.
Okay. So see, a DNA sequence like this, it has a pattern. So after A, C is going to come. After C, C is going to come. Some change is going to happen like this. If we can process this with a Markov chain, then A to A to T, T to C, so on. Now heart pulse, it's again going to show some pattern. You can see it is going to be stable here. There is a spike and there is a dip, again a spike, again it comes to the normal. So there are some changes happening. Normal, high, low, something like that. We can process this also with a Markov chain. Brain activity has a pattern like this. Again, you can see it is very much concentrated, it has peaked, it has reduced, all this. Again, dividing this into few number of states, we can process. So these are some of the applications we can find. So some details of the applications are there, which I'm not going into detail because I think my time is due. Can I continue for a few more minutes?
Yes, madam.
Okay. So I'll try to explain whatever possible. Now this DNA sequence I'll explain. The rest of the applications I'm not that familiar. So little bit I'll give a detail. Now here you can see there is a sequence from A to C. There are 4 states A, C, G, T. Looking at this pattern, we can assess from A it is always going to change to C, or from A it is going to change to T, or A it is going to change to G. There is a possibility of changing to all the 3. So here, after how many steps A is going to change to T, that will be fixed. After how many steps A is going to become C is also going to be fixed. So based on that, some probability can be assessed. So now there is a pattern AGCT is taken. From A to A it will remain, then it will go to T, then it will come back to C. So at time step T, it is at A, time step T plus 1, it is going to be stay at A, then it is going to change to T, etc. So this type of pattern can be assessed. We will know what will be the sequence. Based on that, probabilities can be assessed. Now here also there are 4 states we can create. That is, one is normal, peak, low, and again normal. So based on this, how many times it's going to peak, how many times it is going to go to the low, etc. And some unwanted patterns come, we can assess that. So you can observe something here. This is discrete, and here both these are continuous. You can see it is continuously changing, and this is also continuously changing. Continuous time, discrete xt is example 2. Example 2 is this DNA process. Continuous to T and continuous xt, it is both example 1 and 4. 1 I did not discuss. 4 is this brain activity. Continuous time, discrete value of x is what is we are having as heart pulse during a surgery. So I think I'm going to stop here. You want to ask any questions, you can ask.
Yes, students having any questions? I think no. Radha madam?
Yeah, actually, it's just out of my own interest. First of all, madam, I congratulate you. It is such a wonderful presentation. Really, I think we are all, we have gained lot of knowledge how Markov chain in practical applications should be used. So many, many thanks for this presentation. I just wanted to know, is there any specific book that can be referred only for Markov chain and Markov process?
I have done all this study from whatever is available in the net only. No
Okay,
particular text I have found.
okay. So
So
no
some material is
explores.
there with me which I can share with you also. Some hard
Okay,
copy is there. I mean,
okay,
some
okay,
PDF I have downloaded which I can share with you.
okay, okay. This see, I think you started with some that rainfall data,
Ah,
no? Some. So, and similarly, I actually came across recently. One of the students had approached me for cyclone data also. Can it be that is matrix, can it be created for cyclone data also? I was actually not able to help out that student. I was not knowing how to do that, but today actually our talk has given a lot of ideas. So can it be done for
there is
cyclone data
something
also?
called hidden Markov chain,
Hmm.
which is usually being adopted for any continuous type of process like the cyclone weather or many computer science applications is being used. I've not gone very much in detail because this is not my field of research,
Hmm.
but some possibility is there.
This cyclone data will come into a discrete study or continuous study?
Discrete data, continuous time it will come.
Okay, okay, okay. Thank you, madam. Thank you so much. Wonderful presentation.
Okay, madam. Behalf of Dayanand Sagar College of Engineering Management, Principal Sir, our HOD Madam, and also all my colleagues, I would like to say thank you, Madam. And also I would like to say thanks for all the participants, I think, which is useful for your application specifically for in engineering. I hope it is helpful for our students. Thank you one and all for present in this session.
Thanks,
Thank
sir.
you. Thank you.
Thank you.